So let's quickly talk about extensions of recurrent neural networks, of extensions of the basic model that we've just seen. So the first one I already discussed about. We can make a forward layer in our recurrent neural network and a backward layer, and in this way we can not only look into the past when making a decision, but also into the future via the backward layer. And the important thing when you have such a model, first of all, it's independent. So the forward and the backward layer do not interact with each other. However, they have each, and therefore, because they do not interact, because they're independent, they have each comes along with its own weight matrices. And you see that here's so the forward layer has a weight matrix, the backward layer has a weight matrix. These are independent, so these are not shared, but of course they are again shared across the time steps. And the same is with the hidden state vector. The forward layer has a weight matrix, the backward layer has a weight matrix, which are not shared, and they are independent, and therefore they are doubled, but they are shared, of course, again across the time steps. And this output, this matrix here, which connects the hidden state with the output, stays. However, it becomes also double in size. So basically, everything is doubled. You have double as many parameters, but you can look into the past and into the future now. And this one here is the completely identical illustration. However, it uses a different notation and it uses a different visualization. We use that because these people have already come up with different visualization of deeper networks, which we will look into now. So you can, of course, not only have one hidden layer, but you can have multiple hidden layers. And if you do so, then your model becomes even more deeper and more complex, and maybe you can solve problems better that have a lot of data. However, what you have to keep in mind is that overfitting may take place. So if you have only little training data, then such a deep network is more prone to overfitting. Another thing that you have to keep in mind is now that those hidden layers are not independent anymore, as they were in the previous in the case with just one hidden layer. Namely, what you have is that, let's say, the hidden layer at depth 2 depends, as you can see here in the visualization, it depends on both the forward and the backward layers in the hidden state vectors at depth 1, right? Because you can see the arrows here. So the first node here is always the forward layer, and the second one is the backward layer. And you see that the forward layer here depends on both the forward outputs and the backward outputs, and the same is true for the backward layer at depth 2, right? It depends on the forward layer at depth 1 and the backward layer at depth 1 also. And you can see this also in the equations here. So you have the forward hidden vector at time step t. So this is time step 1, 2, 3, 4. So at time step t at layer I depends on, first of all, it depends on the hidden state vector at time step t minus 1. So you have t here, it depends on t minus 1, the previous time step in the same layer in I, but also it depends on ht, and ht is the concatenation. Here this h is the concatenation of the forward and the backward layer. It depends on ht at the same time step here, but in the previous depth I minus 1, right? So this is this you have to keep in mind, but actually this is exactly the same as you had with one layer. Just in this case with one layer, it was the output depended on the forward and the backward layers, and here you have that each hidden layer at each depth depends on the forward and the backward, right? On the forward and backward of the previous depth, in addition to the previous time step at the same depth. Okay, what you can additionally add is you can add forward connections at the output. So why would you want to do that? It's usually good to know which prediction the model made in the previous time step. when you make a current prediction. And therefore, these additional matrices here, they may be useful. They can be especially useful in particular NLP problem, such as named entity recognition, where you have a bioscheme, where you annotate whether each element in a sequence begins a new entity, it continues an entity, or it's not an entity. So an entity could be Bill Gates, Angela Merkel, or I don't know, Microsoft, right? These could be entities. Maybe you want to identify these entities. So each element in the sequence, you would give a B, I, or O label. For example, Angela Merkel is eating, right? So you would give is eating an O label, because that's not part of the named entity, and Angela you would give a B label because it begins the named entity, and Merkel you would give an I label because it continues the entity. And then you have restrictions such as that after an O can never follow an I, right? Because you always have to start an entity. You cannot just continue an entity. And such relationships are usually so you get better performances if you have such connections to the previous predictions that you made. Of course, you have total liberty in how you want to connect your network. You could also make these connections point to some different layer in your hidden network, like the previous hidden layer, or like one hidden layer down here, or it could also just go to the input, right? So you could also say, previously I have now this current token here, and I have the previous decision here, and now I want to make a new decision. So you are totally free in making your design choices here. And of course, now the question is that may pop up during some exercises or exams: how would the equations look like if you have such additional matrices in your network that connect the output to some element in the network? And what has become popular in NLP, like around 2016, that was 2016 to 2018, that people did not use these matrices, these forward connections, but they used something called conditional random field, which we're not going to discuss at all here. But conditional random fields, this is a particular graphical model, and the solutions that are being calculated are not just given by like a vector matrix multiplication, but it solves some optimization problem that in a sense computes an optimum output sequence given the constraints of the conditional random field. So there are different conditional random fields, like lower order, linear chain, higher order, and these make different modeling assumptions, but the essence is that the output sequence that is being calculated is optimal given the assumptions that each of those model makes. Whereas if you have these forward layers, you have no such optimality guarantee, so to speak. So this is a typical model that was very popular in 2016. So that's already a long time ago, but this was the state of the art by then. What these people had is they had an input sequence, such as we are playing soccer. They wanted to predict the, let's say, part of speeches. So the first one is a pronoun, or a proper, it's a pronoun. The second one is a verb, then another verb, and then that's a normal noun. It's soccer, it's not a named entity. It's not a proper noun such as Angela, but it's a standard noun, a normal noun, soccer. And what you have, you feed that through a forward layer and a backward layer of a recurrent neural network. In this case, they use LSTMs, which we will see later, but basically that's a forward and backward layer of RNN. And the input representation was given by a word embedding. So you looked up your word embeddings in whatever word embedding file or word embedding techniques you were using. And you would additionally, these models would additionally produce a character representation. So what's a character representation? Basically, it looks into the word playing and builds a character representation of playing. I mean, one architecture that you've already seen that's doing that is fast text, for example. So it takes the word playing and then makes a representation of the word playing that takes the characters into account that occur in the word. So if you have a misspelling here, two Y's, for example, it would still give a good representation, an adequate representation. And of course, you could just use fast text here. But at the time these models were developed, fast text was also developed in the same year. So these people were not aware. So what they did instead is they learned the character representation on the specific task. So, and how they would do that is they would again model this, for example, with a small RNN. So they have an RNN on the character level, and from this RNN they get a representation of the word. But this representation exactly depends on all the characters, right? And so you have not only a word-based representation, like from word to vec, but also one that's coming that uses all of the character information in any given word. So why is that helpful? Of course, we already saw that in fast text when we were briefly discussing fast text. Why is that helpful? Because at test time, when you see a new data example, it may be a spelling error, or it may be a word that you have never seen in the training data, but that's closely related. That's particularly the case for other languages than English. Let's say German, you have, for verbs, you have a lot of variation, like du sagst, er sagt, sie sagt, wir sagen. So you have these different morphological variants, and maybe you don't see all of them in the training data, but they are closely related. But when you see a new variant, it may be closely related to a variant that you've seen in the training data, and then you can still assign this variant a good word representation, which you cannot do if you're just using word-to-vec representations and your word and your new word is not in the word-to-vec embedding file. Let's now talk about applications of recurrent neural networks for sequence tagging and classification tasks. So the standard application scenario of recurrent neural networks is so-called sequence tagging, or also known as sequence labeling, where we have a temporal sequence, let's say a time series or a sequence of words. Then we want to classify each element of the sequence, right? So we have our inputs x1, x2, x3, x4, etc., and we want to classify each element in the sequence. That's the standard application scenario. But of course, we can also use RNNs for doing a classification, where, for example, we have a sentence as input or a document, and at the end we want to output a label for the whole sentence or for the whole document. For example, we could want to classify the document in whether it is about sports, politics, or something else, or we could want to classify a sentence whether it's positive, negative, or neutral. And in this case, bear in mind that we would use the last hidden layer as basis for the label, because in the last hidden layer we have seen the whole input sequence. So these are two model application scenarios of RNNs. And where do you find code for RNNs? There are really many implementations out there. Most of them have been produced in the years 2016 and 2017. I list a couple of implementations which you could directly use. Most of them are pretty similar in terms of architecture. Most of them are bidirectional. They use, as instances of RNNs, they use LSTMs, which we will see later in the lecture. They have these conditional random fields on top, which account for label dependencies, and they have representations on the level for each word. They have representations for each word that are based on the characters of the words, and these representations have usually been built using a convolutional neural network, CNN, which we will see in the next lecture. But of course, you could also use another RNN to build the character level representation. For for no good reasons, the term wireless DMC and NCRF has become popular to describe these kind of architectures. If you want to use these architectures, feel free to do so, but keep in mind that they are a couple of years old, and most people today would probably not use them anymore for doing state-of-the-art implementations, but they would use, for example, BERT directly, or some of the improvements of BERT that have been produced in the last couple of months. So where can we apply RNNs in natural language processing? So we have said that the RNNs are natural forms for sequence labeling. So what is a sequence labeling task in natural language processing? Well, one of the most popular sequence labeling tasks is post-tagging, where we have the inputs X as a sequence of words, and the labels Y is the corresponding sequence of labels for each word, where the labels are the part of speeches or word classes. So we would be a pronoun, love would be a verb, etc., etc. So what is the label space here? Well, it's a set of part of speeches that are available in the classification scheme that has been set up by those people who have created the data set. So there are of course different such label spaces and classification schemes in different languages, but even in English there may be several different ones that use different kinds of categorizations. So you could have a very fine-grained scheme that maybe comprises 100 or even up to 1,000 or even more than that labels, or you could have a very coarse-grained label set with maybe only 10 to 20 labels, right? This really depends on the linguists or the NLP people that have created those data sets. And the input space is, of course, sequences over natural language words. So the axis is words in natural language, depending on which natural language you are looking at. In this case, it is English. And of course, we do not only have one word, but we have sequences of words, and those would typically be represented as embeddings. Then another one which I talked about before is named entity recognition, where you want to recognize named entities, and these named entities could be persons, or they could be companies, or they could be countries or something like this. Again, the input is the same. We have sequences of words in a natural language, maybe encoded as embeddings, and the output space consists, in the minimal case, of just 3 different labels, namely B, I, and O. That's also why it's called bio-tagging. So B stands for beginning, I stands for inside, and O stands for outside. And the B marks the beginning of a named entity, the I marks the continuation, and the O marks that this is not part of a named entity. But then, of course, you have this coarse-grained label set consisting of just 3 labels, but you can make this more complex by attaching some subcategorization for each BIO label, namely it could be a person, it could be a location, it could be a company. So you can again make this as complex as you want. Another instantiation is, for example, on the character level. You can also do character level applications for RNNs. One sample case would be grapheme to phoneme conversion, where you want to transcribe a letter form such as shoe into its phonetic representation shu, which is kind of which directly indicates how to pronounce this word, right? There are different languages such as English, which have very weird association of pronunciation and writing, and in such languages it would actually be good if the written form would be converted into something which is more readable. The input in this case would be all sequences of characters encoded as either character embeddings or just one-hot embeddings. So characters are not rare, are not sparse usually, so there are maybe only 20 to 100 characters, so it's not necessarily a requirement to use embeddings for them. We can also just use one-hot vectors because we will probably have seen all of the possible characters in the training data. And then get a good representation just by learning them on the task at hand. And the output space would be a phonetic alphabet, a corresponding phonetic alphabet. For example, a standard phonetic alphabet is IPA, the International Phonetic Alphabet, which you can also see if you go to Wikipedia. So some, especially names of politicians and other famous people are given in IPA transcription, and you would add one special symbol if there is no direct correspondence. For example, between C and H, there's in this case no corresponding output, or the H here, which is just has no well, it's actually dropped from the output, right? So it has no corresponding phonetic symbol, so you would indicate this here with such a dropping symbol. And of course, you could do other things on the character level, such as lemmatization, where you transcribe an inflected form into its lemma form. And the final application that we look at is language modeling, where the input space and the output space are identical, except that the input space is given by embeddings and the output space is given by one-hot vectors. So this is also for you important to note that even though we predict words at the output, we will probably not, or usually not, predict embeddings, because if we wanted to predict embeddings, then it would not be clear which actual word is meant by that embedding. Of course, we could say we predict some embedding, which is maybe not an actual word, and then we choose the nearest word corresponding to that embedding, but that is not usually what people do. Also because then we could not use cross-entropy loss in a meaningful way, because there's no probability distribution coming out if we predict an embedding. So people are not usually doing that, so people predict one-hot vectors that correspond to the words. And in language modeling, the task is to predict the next word, right? So for each input sequence, we want to predict the next word, and we want to predict the next word because in this case, we can model the probability of the next word given the history of words, and in the factorization of the joint probability, we have these conditional probabilities. So we want to model them. We want to model these conditional probabilities by the setup of our task.